Welcome again to one of Dr. Viv's graduate classical mechanics videos. This is the 15th in the series. So last time we used variational calculus in the previous video, number 14, to derive the Euler-Lagrange equations as well as the Hamiltonian equations. What we shall do this time is to have more fun with the variational calculus problems. This class of problems was introduced by mathematicians like Bernoulli, to some extent by Newton. I'll tell you more about Newton during the next video when we shall discuss the really famous problem known as the Brachistochrone problem. In this video, we'll try to get a handle on how to use variational calculus to set up simple problems and actually solve one of the simplest of all problems, which is to show that the shortest distance between 2 points is a straight line. I've written it in a slightly more fancy way. Show that of all curves connecting 2 points on a plane, a straight line is the shortest. So this problem has got many solutions, including geometrical ones, but we want to use variational calculus. We shall take 2 steps to do it. The first step is to show that the straight line is indeed the optimum or extremum solution. And then we shall go ahead to prove that that optimal solution is in fact the minimum solution. And that will involve the global data in the form of the endpoints of the variation. So let's proceed to do this. Our starting point is the Euler equation. So let's recall what that is. So the task is to take a function of an unknown function y. So y as a function of x is our target. We're trying to find it. So assume there's another function of the function y, its derivatives, and x. This object is called a functional because it's a function of a function. So this is the sought for function, and under what conditions will that functional be extremized? So Euler asked the question, let S be equal to the integral from 1 to 2, capital F of y, y prime, x, dx. Here 1 is the initial point, and 2 is the final point. So what we're trying to ask is find the function y of x such that this is extremized. Now, for extremization of the quantity known as S, capital S is called the action in physics. So we'll stick with that terminology. So the action has to be extremized. Strictly speaking, the action is the integral of the Lagrangian dt, but I shall call it the action within quotes if you like, because it's the same family. Euler said that this action is extremized if we take what's known as the functional derivative, that is given as follows: d by d epsilon evaluated at epsilon equal to 0 of s as a function of y plus epsilon eta. So I want to make it clear that this s here is a function of y. What we're doing is we're perturbing the y a little bit by this new function eta of x, such that eta of 1 is equal to eta of 2 equal to 0. So that is our idea. So if you perturb this, then you get what's known as the first variation formula of Euler. We derived this last time, so I won't go through the derivation. The Euler equation, which is the solution to the above problem, is the following. The partial derivative of f with respect to y is d by dx of the partial derivative of f with respect to y prime. So that's the important Euler equation. There's a class of Euler problems which are called cyclic. So let's define what a cyclic problem is. A problem is called cyclic if the functional, which generally can depend on y, its derivative, and x, does not depend on y. It only depends on y prime and x. The cyclical terminology is inspired by the notion of a cyclic coordinate in Lagrangian mechanics. In Lagrangian mechanics, if the Lagrangian is independent of a coordinate, the corresponding momentum is conserved. So we're going to see that here also. If a coordinate is cyclic, then clearly the derivative of f with respect to y will be 0. Why is that? Because there is no y in the functional. Now, if you substitute that into the Euler equation, I get that d by dx of del f over del y prime must also be equal to 0. And if that is equal to 0, then that implies that del f by del y prime is a constant. We're going to be using this in doing this problem. So let us go ahead and set up the problem now. Our setting is the two-dimensional plane, although I should point out that this problem is quite general. You don't have to stick to 2 dimensions. You can go to n-dimensional flat space. And I will tell you about the generalizations to curved space as I set up the problem. Curved space takes us a little bit further into differential geometry and general relativity. So I will not quite do that since we'll run out of time. I'll keep this cyclic property for reference nearby. So let us set up the problem. We have to look at a portion of the plane. I'll just draw it as a rectangle. And we have point 1 here, point 2 there. Now, for the moment, we do not know that the answer is a straight line. So what we can do is imagine that there's some crazy curve like this, and we wish to find that curve. Let's try to find that curve gamma. That curve gamma will be found in the form of y as a function of x. And we have to find that curve which makes this blue line the shortest possible. All right, the endpoint 1, because we are working in the coordinate system x and y, this is R2. The x coordinate could be to the right and the y coordinate could be up. So the coordinate 1 corresponds to x1, y1, and the coordinate 2 corresponds to x2, y2. The action functional is that of a length functional. So we'll call this the length functional. Length function. And the length function is a function of the path y. And that's going to be the integral from 1 to 2 d of the arc length s. So that ds is the arc length So if you take a small portion of this curve here, the length of that portion is ds. Now you're going to sum that up over the entire curve and get your arc length, or the length of the curve, which is a function of the curve that you choose. So you write it as L square brackets y. So now we have to find a formula for ds. So ds is your arc length. Or more specifically, it's called the arc length differential. What kind of formula can we write for that? Now, in general, you have to write a formula that looks like this. ds squared is gij dxi dxj, where gij is known as the metric tensor. Now, if you did this and proceeded to solve the complicated problem of finding the extremal value of the arc length, you will end up with the equations known as the geodesic equations. And I just want to comment that these look like this. Del tt equal to 0. That's the equation of a geodesic. And then once you have that, you can subsequently solve for the actual geodesics by putting the boundary values. So this is the subject of general relativity and differential geometry. What is that quantity t? T stands for the tangent vector at any given point of the curve. So if you're interested, please read up on this geodesic equation on your own. So t is the tangent vector, and this del symbol is known as the covariant derivative. Although it's interesting, it's a little bit tangential to our line of thought in this course, so I won't pursue general relativity anymore. In our example, the metric tensor is a very simple one because the space is flat. If space is curved, then metric tensor can be more complicated. For example, you can have a sphere or something that looks like a Pringles potato chip with positive curvature in one direction, negative curvature in the other direction. So these metric tensors can be complicated. So R2 is flat. If you have a space that's flat, the metric tensor takes a very simple form. ds squared is eta ij dxi dxj, where eta ij is just the Kronecker delta. I use eta ij because that's the symbol, that's the usual metric one uses in general relativity for a flat space-time. In reality, eta ij has got both space and time. However, I can't switch notations that easily, so I'm going to call it eta ij instead of delta ij, which really is what it is. So if you really want to be careful about things, this eta ij is just delta ij for R2. Well, what does that mean? Normally, this would have four terms: dx1 times eta 1. Let me just go ahead and write that. The summation notation of Einstein is used, so we sum over repeated indices. Because eta 1, 2, and eta 2, 1 are 0, these two terms don't contribute, and so we just left with those two terms. Well, dx1 is just dx, and dx2 is just dy, so this is just dx squared plus dy squared. Well, that is something you could have guessed. If you have a two-dimensional situation, then the arc length ds looks like that. That's dx, and that's dy. And you have the infinitesimal version of the Pythagorean theorem, ds squared equals dx squared plus dy squared. Not too difficult to simply guess. This is sometimes written as follows. We write this as dx squared times 1 plus dy over dx, the whole thing squared. And that makes it a little more user-friendly because y is the curve that we're interested in. Okay, we are interested in y as a function of x. So you do things to y. For example, you can take the derivative of y with respect to x. So dy by dx is readily known. Now we take the square root of both sides. The positive square root is sufficient because length is positive. So ds is just dx times the square root of 1 plus dy by dx, I will write as y prime. So it's just 1 plus y prime squared. So we have identified what our functional is. The functional is whatever appears under the integral sign. We said that ds appears under the integral sign, but ds is in fact equal to that. Let us write our length functional with this. So I'm going to get the arc length functional L is equal to the integral from 1 to 2 ds, which is this. So it's square root of 1 plus y prime squared dx. And this immediately tells us that our function of functional, which is f of y, y prime, and x, is square root of 1 plus y prime squared. Observe that this is not dependent on y. Because it's not dependent on y, we can use the cyclic property. The cyclic property says if the functional is a function of only y prime and x, which it is in this case, actually it's not even a function of x, it's just a function of y prime, then the following quantity is conserved. So we can move directly to the conserved quantity in this case. Let's do that. So by the cyclic property, I have del f by del y prime is constant. I'll call the constant c, not to be confused with the speed of light. It's just a constant. So I'll differentiate the object. F is just that. When I differentiate the square root function, I get 1/2 and then 1 plus y prime squared to the power minus 1/2. But then I have to use the chain rule and differentiate the inside function. So I get 2y prime equals c. The 2 cancels out. I can solve for y prime by moving this to the other side. So I get c times the square root of 1 plus y prime squared. Now I square both sides. So I get y prime squared equals c squared times 1 plus y prime squared, which is c squared plus c squared y prime squared. I can now solve for y prime squared. I'll take this to the left side. So I get y prime squared 1 minus c squared equals c squared. And then I'll divide both sides and take the square root. I'll do that in one step. So I'm going to get y prime equals plus or minus c divided by the square root of 1 minus c squared. That's it. In other words, it's a constant. I'm going to call this constant in the time-honored tradition of plus or minus m. You can see where this is going. That m is the slope of a straight line. If I now integrate, I get, this is dy by dx. So if I integrate it, I'm going to get y equals plus or minus mx, because the derivative of a linear function is a constant, plus of course a constant of integration, which I'm going to call b. the y-intercept. So this is our famous straight line. Now, in any variational calculus problem, it's good to have the local solution. So what we have done is basically found the extremum or the local solution, which is that of a straight line. We have to do two things now. We have to use the boundary conditions between 1 and 2 to actually solve for the constants m or plus or minus m and b. That's the first thing. And the second thing is to establish the globality. So there's a subtlety here. If when you're imposing the boundary condition, some weird things can happen. I want to just spend a little time on it because in some cases, especially in soap film theory, you can have the local solution but not the global solution. Let me show you what I mean. Suppose I have two wire frames of different radii, and I place them a certain distance apart, and I'm looking for a soap film between them. So the solution for the minimal surface area is some curve like this, okay? So there are three things I can vary about this situation. There's your R1, the radius of the first hoop, R2, the radius of the second hoop, and then the distance between the two hoops, D. If you can have a soap film that looks like that. Now, but if you took the distance D too far away, then this solution is no longer stable. So for certain values of R1, R2, and D, this is not the proper solution. So boundary conditions can and will influence your final answer. So if your curves are really far away, you can show under certain conditions. This is actually a very complicated problem known as Plateau's problem. After the Belgian physicist Plateau, you can show the solution looks more like this. So it degenerates into two small surfaces connected by a singularity, which is a line. So you can show all these weird phenomena happen if you try to impose the boundary condition upon this extremal solution. In our case, fortunately, we don't have such phenomena, so we are going to have a rather smooth journey trying to determine our constants of integration, which is m and b. So all we have to do is impose the boundary conditions for this problem. The point 1, I have y1 equals plus or minus m x1 plus b. At the point 2, I'm going to have y2 equals plus or minus m x2 plus b. Now the best way to solve for m, or rather plus or minus m, is to simply subtract the two equations. Then I'm going to get y1 minus y2 equals plus or minus m times x1 minus x2. When I subtract the two equations, the b cancels out. So this gives me the value of plus or minus m. It's just y1 minus y2 divided by x1 minus x2. Now to find the constant b, you can of course substitute this into one of the equations and solve it, but that leads to, I think, messy things. So I always like to do something slightly different. I'll multiply the first equation by x2. So I'm going to get plus or minus m x1 x2 plus bx2. And I'll multiply the second equation by x1. I'm trying to get rid of m. So x1 y2 is going to be plus or minus m x2 x1 plus bx1. Well, x1 x2 is the same as x2 x1. So if I subtract these two equations, which I'll do next, I'm going to get my value of b. So x2 y1 minus x1 y2 is equal to b times x2 minus x1. So here I've subtracted the two equations. And that immediately gives me my constant b. And so we have found our solution, the optimum curve that achieves the objective. I'll call that gamma naught because the naught indicates it's optimal. So gamma naught is defined by the following function. It's y1 minus y2 over x1 minus x2 times x plus x2 y1 minus x1 y2 over x2 minus x1. So that's our answer to this problem. That's the curve joining the 2 points, x1, y1, and x2, y2. That is the shortest possible. Now, I want to talk a little bit about proving that something is a minimum. Now, in traditional calculus, so let me just do a little bit of analogy here. In traditional calculus, you have two methods to prove that a given extremum is either a maximum or a minimum. The first is called the first derivative test. Here, what you do is you take the critical value, and in calculus, you just have a function f of x, and you're trying to extremize it, like maximize or minimize it, and so you have the critical value x sub c. The first derivative test, you see what happens when you add or subtract some quantity epsilon from x sub c, the critical value. If it is bigger than f of x sub c, then you have a local maximum. Sorry, if it's bigger, then it's the local minimum. The reason is because of this. Draw a little picture here. That's x sub c, and that's the value of the function at x sub c. If either the function at x sub c minus epsilon or the function at x sub c plus epsilon is taller or higher, then it means that x sub c is a local minimum. But if you have a shape like this, and the value of x sub c is over there, then either if you go to the left or to the right, in other words, if you go to x sub c minus epsilon or x sub c plus epsilon, you're going to find for the local maximum that f of x sub c plus or minus epsilon is less than f of x sub c. So this is called the first derivative test. The second derivative test in traditional calculus, you just take another derivative and evaluate it at the critical point. So del 2f by del x squared evaluated at the critical point can either be less than 0. If it's less than 0, it's the local maximum. And it's the condition for concave down. That's the picture over here. It's concave down. It's palm down. If it's bigger than 0, then it's a local minimum or concave up. All right, now how does all this translate into the calculus of variations? We are not in traditional calculus anymore. We are varying entire paths and seeing their effect on a certain quantity that is being extremized. So in the calculus of variations, the analogy is very similar. You have two methods, the first variation and the second variation. And here, the first derivative test is what we're going to use in this thing. So in calculus of variations, I just want to point out a little bit more at this stage rather than simply solving the problem, because this will set the stage for the future. The first derivative test what you do is you take a nearby curve, y tilde, which is equal to y of x, the curve that you actually found, the critical value, plus epsilon eta of x, where eta is any arbitrary curve, completely arbitrary, not fixed at all. In other words, you're not at liberty to assume what eta is. You just call it some function. Epsilon is your parameter that you can actually control. The strength of epsilon can be controlled, and we'll take the epsilon to always be much less than 1. What this allows us to do is to truncate our calculations to second, sometimes third order, but not usually second order. And then this length functional with y tilde stuck in, if you can show that that is bigger than Ly, we have our local minimum. So this is the analog of the first derivative test, where we are showing local minimum like this, where y tilde is y critical plus, here we just had epsilon, but here you have plus epsilon times an arbitrary function. Okay, so that's what we're going to use. Now, what about the second derivative test? What is the analog of the second derivative test in variational calculus? What you're going to do there is, having found the critical curves, you're going to go to nearby critical curves and see which critical curve is the smaller one. So this is a more complicated thing, and it leads to what is called Jacobi fields. And we'll encounter these later in the course. I'm thinking in the video numbers 20s, some late 20s, we'll talk about the Hamilton-Jacobi equation and applications thereof. So it's all coming from calculus of variations. Let's go back to this problem and get our tilde set up. So our action function L of y tilde is going to be the integral from 1 to 2, the square root of 1 plus y tilde prime squared dx. That's our original length functional, but now we're going to perturb it. So what am I doing? Let's go back to our, I'll redraw this square I drew earlier. So you have points 1 and 2, and we have established for sure that the extremal path is a straight line. Now, what we're doing actually would seem very silly to most people. We are trying to perturb this path, and the way we are doing it is like this. We're using a function eta, which can, the eta function can go this way or this way, and we are asking, is this path longer? Well, anyone who's got proper eyesight knows that this purple line is longer than the blue line, but how do you prove it mathematically is the thing. So this is a perturbed path, which I'm going to call y tilde, and that's our critical path, y critical, given by this. All right, let us set up this, let's evaluate what that thing is, okay? And then we'll perform the approximations after that. So there's a lot of fine points in a calculation like this. Let's look at some of the fine points. 1 plus y tilde prime squared is, by definition, because y tilde is given like that. I'm going to stop writing critical. I'll just write it as y, like I've written there. So it's going to be 1 plus y prime plus epsilon eta prime, and the whole thing is squared. Okay, now you just have to use the a plus b squared formula. And so this becomes 1 plus y prime squared plus 2 y prime epsilon eta prime plus epsilon squared eta prime squared. We want to make use of the fact that this is a critical curve. So we shall take this out, 1 plus y prime squared outside, and then let's see what's left. There's going to be 1 plus all this stuff. that's not taken outside, divided by what you took outside. So far, everything is exact, and I have not made any approximations whatsoever. It is now that I have to make some approximations because this thing is impossible to get an exact expression out of this. So we're going to use the following approximation, known popularly as the binomial theorem approximation of Newton, or BTA. Newton's binomial theorem is this long theorem, but if you truncate it to the first order, it's called the BTA to order 1. And the BTA to order 1 says you just keep the first term, 1 plus nx. If you feel that this is too little and your problem may suffer as a result of using just BTA to O1, then you go ahead and do BTA to O2. But in this problem, BTA to O1 is plenty. So let us go ahead and implement that. My x is all of this. My n is half. Okay, that's 1 plus x to the power half. So I'm going to get 1 plus half x. So the calculation is 1 plus y tilde prime squared is approximately equal, and here I'll put BTA because I'm using the binomial theorem approximation, the square root of 1 plus y prime squared times 1 plus 2y prime epsilon eta prime, the numerator, divided by n, which is half, so I'll put the 2 downstairs, 1 plus y prime squared. And so that's our nice looking result. So now let's, this is a sum of 3 terms, so let's write those 3 terms. So that's going to be the square root of 1 plus y prime squared. Then I take 1 plus y prime squared and multiply it here. Because it's a square root and that's no square root, I get a square root in the denominator. The 2's cancel out for the middle term. So I get y prime epsilon eta prime over the square root of 1 plus y prime squared. And lastly, the last term is epsilon squared eta prime squared over 2 times, once again, the square root 1 plus y prime squared. Now remember, I told you this eta function can go this way and that way. So eta prime can sometimes be positive and sometimes be negative. So this term here, you don't know what it's going to become. Is it positive or negative? We don't know. So that makes a big impact, because if this term is very negative, then this could actually prove that the purple line has less length than the blue line. And that won't be good for us. So let's focus on this term. This term for sure is positive. So epsilon squared, whether epsilon is positive or negative, epsilon squared is positive. Whether eta prime, the derivative of this eta, whether it's positive or not, eta prime squared is always positive, and the denominator is guaranteed positive. So let's call this a positive quantity, q squared. This term here is the term that is we're not sure about. So let's call this the iffy term. The iffy term can go either positive or negative. So the iffy term needs to be evaluated. Well, when you do the action functional, you're actually evaluating it between 2 points. So you're going to have integral 1 to 2, the square root of 1 plus y prime squared dx, plus the iffy term, which is going to be 1 to 2 y prime epsilon eta prime over the square root of 1 plus y prime squared dx, and then your q squared term, which is guaranteed positive. So I'll just write this as integral 1 to 2 q squared dx. So that's guaranteed positive. But what about this? So let's evaluate the phi term. So the phi term is 1 to 2 y prime epsilon eta prime over the square root of 1 plus y prime squared dx. But this y prime is the critical value. So we are looking at the critical curve, that critical curve there, which is the same as the critical curve here. So y prime is just plus or minus m. It's right there. Y prime is plus or minus m. So let's use those things. So let's evaluate this. I get plus or minus m epsilon divided by the square root of 1 plus m squared integral 1 to 2 eta prime, which is d eta by dx, dx. Well, d eta by dx, dx is just d eta. And when you integrate d eta, you just get eta at the final point minus eta at the initial point by the fundamental theorem of calculus. So this is just a bunch of constants outside times eta at the final point minus eta at the initial point. But eta at the final point and eta at the initial point are both 0. That's one of the things we have in variational calculus. You cannot vary the endpoints. You can only vary, the endpoints have to remain fixed. You can only vary what's in between. So I think I have a picture there. You cannot vary the endpoints. The endpoints are fixed, okay? So this just vanishes. Some authors like to think that this is more general than the endpoints being fixed. You can actually move the endpoints provided you move the right endpoint as much as the left endpoint. But I won't get into that additional degree of fineness. All we need is the phi term simply vanishes. And that's really our proof. L of y tilde is, this is just L of y plus a positive term, which I'm calling that term p squared. And that conclusively proves that L of y tilde is bigger than L of y, thereby establishing the absolute minimum nature of the straight line. Absolute, sometimes called global minimum. Now, is this kind of proof always true? The answer is no. You encounter problems in other geometries. So let me just point out what happens in a very interesting case, because this is relevant to things like airline travel. If you have a sphere, then of course you know that there are antipodal points on a sphere, such as the North Pole and the South Pole. But you don't, that's not the only two antipodal points. You can have any 2 points connected by a diameter. I'll just use north and south because it's convenient. Well, everybody knows that airlines to greater or lesser degree fly in a curved path known as a geodesic. There are some restrictions. For example, I just recently learned that all aircraft have to be within 1,000 miles of land, even if they're flying on a geodesic. So they have to sometimes alter the geodesic a little bit for various safety reasons, I guess. So if you're flying between the North Pole and some destination, let's call it P, then you're going to take this geodesic, which is a section of the Great Circle. But which section? You can also, if you're not very careful, be flying like this. That's certainly the long way around. You can go from the North Pole to the South Pole and then from the South Pole to P. Both of these are geodesics. And this criterion of first derivative criterion will not discriminate between what is called a maximal geodesic and a minimal geodesic. This is a minimal geodesic. And that's a maximal geodesic. So you've got to be careful. That's one way to pull it off. And the second derivative test always fails between the North and the South Pole. And you can see why that is. Between the North and the South Pole is a very special circumstance. All geodesics are either maximal or minimal. So you can go from the North Pole to the South Pole either this way or that way. And if you do it either way, you're going to get the same result. So all geodesics are neither maximal nor minimal. It's like the failure of the second derivative test. And that happens because a certain vector field that joins these 2 points vanishes. Zeta is known as the Jacobi vector field. And it's a vector field that governs variations of geodesics themselves. And if in more than 2 points, if zeta vanishes, then you're supposed to have a pair of conjugate points. And that if once you have a pair of conjugate points and you have a geodesic that goes through the conjugate points, then your maximal and minimality criteria get messed up. And that is the deep reason why you cannot use the first variation or the second variation ideas to deal with these 2 classes of geodesics. I'll just leave that advanced comment for those hanging for those who want to pursue it. So I'll just say that the NS is a pair of conjugate points. If you're really interested, just Google conjugate points and you can find out everything about it in differential geometry. Well, that's the end of this problem.